Now here we talk about Coulomb damping or the dry friction damping. So the dry friction damping. So this mass is actually moving on a rough surface, and the normal reaction on this mass from this surface is N, and the friction force is mu N or mu mg. So, and as the direction changes, the friction force, the direction of the friction force changes. The friction force is constant, but the direction of it changes depending on the direction of motion. So it is Fd into Fd is mu n, and sine, the sine function, the sine x dot is equal to 1 when x dot. So sine x dot is equal to 1 for x dot greater than 0, and sine x dot is equal to minus 1 for x dot less than 0. So if you write down the equation, so this is the equation, or mx double dot plus Fd sine x dot plus kx is equal to 0. So this is actually a non-linear equation. So anyway, so we won't attempt to directly solve this equation, but this is a non-linear equation, because in place of cx dot, where c is a constant, we are getting this term sine x dot sine x dot can also be written as x dot by magnitude of x dot. So if you put it here, Fd x dot by magnitude of x dot, so this becomes mx double dot plus Fd. Fd is a constant, and here 1 by the magnitude of x dot into x dot plus kx equal to c. And if you compare this with mx double dot plus cx dot plus kx equal to c, then you see kx equal to 0, then this c is not a constant here, rather c is also dependent on x dot. That makes the equation non-linear. So you can solve this equation using numerical methods. In MATLAB you can solve it. Anyway, we are not attempting to solve this equation here. Rather, suppose due to this damping, so suppose this is the pattern of the displacement, so the displacement amplitudes decrease. Now we'll try to see how these amplitudes decrease. So one thing, so if this is the displacement graph, approximate velocity, this is an approximate velocity graph, so you can draw it using dotted line. So you can draw it like dotted lines like this, because this is just an approximation. You do not know the exact shape, so you can draw it in dotted if you wish. Yes, and see here you understand that So here this diagram is actually the slope of the displacement diagram. So this is the maximum slope, so velocity is maximum, and here the slope is 0, so velocity is 0. Again here the slope is 0, so velocity is 0, and here negative maximum, so velocity is negative maximum. So like this you can plot the velocity diagram. And this damping force, as long as the velocity is positive, the damping force remains constant. Then as the velocity changes sign, because the direction of motion is actually dependent on the velocity of motion. When the velocity becomes negative, that means it is moving in the negative x direction. So, and when the velocity is again positive, that means it is moving in the rightward direction. If we take x rightward positive, so this is actually the direction depends on direction of motion, whether it is moving from left to right or right to left, that depends on velocity. From here to here it is moving from left to right, and here to here it is moving from right to left. Okay, and here again left to right, then right to left. So suppose in this region it is moving from right to left. That means here what happens, it has reached its extreme right position. Now it is slowly going towards the mean position, then it is going towards the extreme left position. That means suppose this is the mass, this is the mass, this is the mean position, this is the extreme right position, and this is the extreme left position. That means it has started from here, it has gone x1 and reached the mean position here, then from here to here it is going in this direction. Then after coming here it will again change direction and go in this way. So, and you see during this portion of motion, from here to here, this portion of the motion from x1, that is from x1 to, sorry, not x2, this is x1 dashed. This is x1. I am again repeating, then this is x1 dashed. So it is here, that means it is here, it has reached its maximum displacement in the rightward direction. Then it is starting its leftward motion. So leftward motion from here to comes to the mean position. So this is the mean position. Then it starts its leftward motion further. So here, and it is coming to the extreme left position, and that is here. And that means from here to here it is moving from right to left. Here to here it is from right to left, and from here to here the sin x dot, fd sin x dot is minus fd. That means actually the direction of the friction force is this way. So friction force is opposing the motion. And what is the amount of energy lost in friction? That is fd into x1 plus x1 dashed. This is the energy dissipated by friction. And what is here the velocity is 0, because here the velocity is 0 and here also the velocity is 0. So all energy is stored in the as potential energy in the spring. So what is the loss of potential energy? Half k. So from x1 dash square to x1 square to x1 dash square. So that means, so x1 minus x1 dashed is equal to twice fd by k. Similarly you can show for, so from here to here, that is from here to here here to here, from here this extreme, that means this left extreme point to right extreme point, now will not reach this point, it will come to a stop left of this point. So when it moves from here to here, so it is moving first here to here, that is x1 dashed, then it will move x2. So this is x1 dashed, it will move x1 dashed, then it will move x2. So this is x2. So anyway, then we get x1 dashed minus x2 for that portion of motion, we get twice ft by k. So if you combine these two, then x1 minus x2 is equal to 4 fd by k. That means these amplitudes they decrease actually linearly. So these amplitudes, so they decrease linearly, because here to here there is a decrease of 4 fd by k. Then from here to the next amplitude, there will be another decrease of 4 fd by k. So since the decreases are same, that is 4 fd by k is the decrease, so that means in Coulomb damping the amplitudes decrease linearly, not in an exponential fashion as it happens in viscous damping. So this is all about Coulomb's damping. So let us stop here, and again we will start with I think now it's time to start forced vibration. So from the next class onwards we'll start forced vibration. So let us stop here.